Okay, it's 4 p.m., so I guess we can start. So, thank you very much for joining the session. I know it's at the end of conference, so it can be challenging, but bear with me for the next 30 minutes. Today, I'd like to show you a few interesting things about what we are cooking up in Hazelcast. For a very long time, and I think that in the community is aware that Hazelcast is a distributed cache, but I think that the project has evolved a lot during last couple of years, and I think that it's lacking awareness. Plus, since I'm pretty close to the core development, I know what we are trying to come up for the future, which is pretty exciting, and I thought I'd like to share it with you. My name is Grzegorz Piwowarek. I write this blog for comprehension.com. I'm the lead architect in Hazelcast, which means I'm working in the CTO's office. Well, technically we don't have a CTO at the moment, but I still work at their office, which means I get to jump into different projects and help wherever help is needed. I also do workshops. By the way, remember that you can ask questions at Slido. So, 2008, this is when first lines of Hazelcast were actually written. The project wasn't yet published, and indeed, it started all as a distributed cache, embedded, Java only, and pretty convenient to use. And I remember my first encounter with Hazelcast was over 10 years ago? Yeah, a long time ago. I went to some conference, still as a student, and there was a booth from Hazelcast, and someone grabbed me and they told me that I can get a free T-shirt only if I agree to have a look at the demo of their product. And I was a student at that time, so 5 minutes for a T-shirt. Well, I could do it all day. It felt like a good deal. So I went for that, and I was amazed. Because the demo was very simple. They created a few instances of an IMAP. That thing suddenly, clustered and was ready to work, and it felt great. But since that time, a huge evolution happened, because at the first step, the base Hazelcast is not just a cache. It evolved into something that's called Operational In-Memory Computing Platform, IMDG, which is pretty much a fancy name for an in-memory storage with a lot of compute capabilities. And once we started growing, embedded in Java wasn't always the main target. The client-server topology appeared, and we needed to start supporting not only Java developers, but also other languages as well. Which means that we got quite a huge number of clients from other languages. And what differentiates IMDG from a cache is a few interesting things. But before we talk about them, let's try to decipher what IMDG actually means. Well, IMDG is a shortcut for in-memory data grid. And when we say in-memory, that usually means no persistence, because the data is stored in RAM. And when someone decides to say that, well, we don't have persistence, but we are in memory, it's not just to say that we just didn't bother to implement persistence, but it's to underline that latency and throughput that you can get from RAM is orders of magnitude better than when it comes to working directly with the HDD. However, 10 years ago, the difference was huge. We would still had those old good disk drives with moving parts, and doing computations using your physical disk drive versus RAM, the difference was huge. But nowadays, the difference between RAM and disk drives gets smaller and smaller. And the new generation of NVMe SSDs is pretty impressive. So when we meant in memory, it means focus on low latency and high throughput. That would be unachievable for hard disk drives. When we mean data, well, obvious part is that we mean storage, because you can store the data. But quite an important aspect is ability to perform computations on that. Imagine you have a cluster of 50 nodes, each node storing 1 gigabyte of data, and now you need to perform some computation on that. So, well, you get this map interface, you get to forage through that, and then, well, forage again to put it back to the cluster after performing some changes. That will probably work in your tests. That will probably work in your local environment. That won't work if you need to suddenly start moving gigabytes of data through the network. But what's the best place where to perform that computation? It's not in your client, the application that's connecting to the cluster, but on the cluster itself. And cluster indeed has quite an impressive computation capabilities. And that last word, grid, it pretty much means that there are multiple processes that can work together as a group, well, forming a cluster. So from the outside, it might feel like you are putting and getting data out of a continuous map, but internally the data is partitioned and backed up, spread over multiple nodes, depending on various internal settings. So that's the part that's really important to keep in mind, that this is just not a replicated single map, but a partitioned data store. And now, usually people start asking questions. Okay, this is cool, but where do I put it in the picture of my system? And the most obvious answer that comes to my mind is that, well, you put it somewhere next to your database, but then when you start thinking about trivial cases like implementing saves and updates by yourself, suddenly you end up facing quite difficult challenges to solve. Because how would that look like? Well, I'm fetching data from a database, and I want to put it in Hazelcast. Okay, but where do I do that? Okay, let's go for the application layer. So there is a flow. I want to read something from Hazelcast cluster, but the data is not there. So then I need to read it from a database or some other data source, and then do an if-else, and then put it into a Hazelcast. What if I do the other way around? What if I want to write something? So I would go and write first to Hazelcast, then to a database. But again, what if one of the writes fails silently? I end up with inconsistencies. Okay, let's start the other way around. So let's we want to write something, we write to database first, and then to Hazelcast. A bit better, because we know that we can make sure that database write succeeds always. But then we are not sure if we've updated Hazelcast, which is a bit better than ending up with permanent inconsistencies. Okay, and as you can see, this generates a bit of trouble in thinking. And the problem is that at the end of the day, you can't have a proper transactional write to two heterogeneous systems. So that's why people came up with different patterns where this can be actually placed. So one of them is a read-through. This kind of makes it a bit easier, because in this pattern, the Hazelcast cluster kind of hides the data source from you. And you would read directly from Hazelcast, and if something is not in Hazelcast, it's Hazelcast that would actually read it from a database and give it right back to you. So the same would work the other way around. So if you want to write, but you don't want to manage the complexity of writing to two heterogeneous systems, well, you can write just to Hazelcast, and Hazelcast will flush it to the database for you. And you might be asking, Greg, but I wanted to use Hazelcast as a cache so that I don't need to write to a database or read from a database. And you are telling me now instead of a one network hop, I need to do two network hops. Well, that's true. That's true, but the reason I'm showing this to you is important to understand the trade-offs. You trade off lower, you get lower complexity for that tiny bit of extra latency. However, if lowest possible latency on writes, for example, is your challenge, then you can go for something like write behind, where you write to something to Hazelcast, and Hazelcast chooses the right moment to batch those writes and set them to a database, which obviously gives you lower latency, but there is some tiny risk that something could go out of sync and fail after flashing the update after some time. Some of you might ask, why would I even use a cache and put it, not locally, but try to access it over the network. And it's a valid concern. However, the first answer would be Hazelcast is not just a cache. Secondly, if you really want to have the slowest possible latency, you can have a cache kind of in a cache available on the client-side level. So if you are willing to trade off, if you are willing to loosen a bit that eventual consistency, you can get really nice low latency because the most access data would be stored, cached directly client-side. But that's just for you to have some, to paint a picture of where you would normally kind of put that. And I covered pretty much caching use cases. And now stuff happened. Cloud happened, containers happened, Kubernetes happened. And suddenly people started using things in a different way. And we needed to adapt. And it starts with very basic and trivial and annoying things, like file-based configuration, which is, well, it's not a big deal. It's not rocket science to write your own XML or YAML file. But if you are running, imagine the frustration that people need to go through when you have your, well, defaults work for you. You need to flip a very tiny switch, and then you need to craft your own XML file and figure out how to mount it, for your ECS or even locally. Again, not a rocket science, but can be annoying at times. Another thing is, once we looked at all those right behind read-through patterns, there is naturally a need to have some code running on the Hazelcast side that's able to read from a database or from any other source and flash those updates. And some of that is actually provided for you out of the box in Hazelcast, but sometimes there is a need to upload your own code to Hazelcast, which is not just challenging because if you are a Java developer, you need to potentially deal with class loading issues, but this is challenging because, well, there's the inconvenience of figuring out how to provision a jar file to make it available for your cluster. Another thing is, in the past, it was quite common that you would have, quite beefed up boxes somewhere in your company's basement, and people would set up, five nodes and live with them permanently, or more. However, in the cloud, if you leave quite a lot of nodes running on the side, you might end up surprised. You might end up dying after seeing your AWS bill. So suddenly, auto-scaling became a thing. So people started trying to figure out how to scale in and scale out Hazelcast clusters, and that sounds like an easy job. But if you start thinking about potential usage patterns and what metrics you would need to look at, suddenly you realize that this is actually a PhD thesis and not just a matter of, if the memory went over that, scale up. If memory went lower than that, scale down. Another thing that was pretty interesting and challenging is that suddenly, and we actually did speak about this during my session today, earlier, if you are in the cloud and in containers, suddenly you are back, sometimes can be back to running on your grandma's computer, because suddenly your machine has one CPU. At least that's how the logical allocation looks like. And the way, for example, Hazelcast works internally, it utilizes architecture called SIDA, which is Staged Event-Driven Architecture, which is a very fancy name to say that there are multiple thread pools and queues between them. So when there's a request coming to a Hazelcast, there will be one thread pool, taking over, just handling the socket. Then it will be passed to another one, and eventually end up with a write or read from a partition. And that's how many software has been running for years, and there's nothing wrong with that. But you need to figure out optimal ratio and sizes of those thread pools, and they depend, for example, on how many CPUs you have locally, or at least what runtime get runtime available processors returns. And now, if your machine tells you I have 32 cores. Okay, we know how to optimize for that. But when your machine tells you you have one core available, Okay, this can be a bit tricky. And one of the biggest challenges from the product perspective was that Java is no longer considered that cool. So people wanted to use Golang, Python, Node.js. But those people sometimes needed to work with the Java code. Because if you wanted to squeeze max out from the performance, you would still need to upload the jar with your own serializers and deserializers, the cluster. So now imagine a Python developer crafting a jar file with custom deserializers, sending it to a cluster and debugging potential class loading issues. Right? So we started tackling all of those issues one by one. And it starts with something that's super easy and trivial. So just like you can do with Spring Boot, you can replace configs using your own env variables. The same you can use with Hazelcast right now. Simple but effective. We started moving into being a polyglot first, which means we kickstarted multiple initiatives. First one being zero config serialization. So now there is no need for extra configuration, uploading your own classes if you want to have optimal performance when serializing, deserializing. This is all happening for you automatically, starting with 5.2, which should be released tomorrow on GeeCON. And suddenly, this removes like 80% of cases where you would normally need to upload Java code. There's just no need for that because this will happen for you. The schema will be derived directly from the object structure just for you and using any language of your choice. Well, that's compatible with Hazelcast. Another thing, so if you wanted to do computation on Hazelcast, well, guess what? You would need to upload more code. So we started developing proper SQL engine so that in the future, I mean, it's not full-blown, it's getting better with every release, but the goal is to replace at least most of the compute capabilities directly with SQL usage. At the end of the day, there's declarative polyglot and all the languages are fine using that. Well, maybe except Java, because we love Hibernate. Another thing is, if you wanted to have this map loading capabilities, like in the read-through stuff, you still needed to sometimes upload your own code. But in 5.2, you are getting the zero code map loader, which means the only thing you need to do is to provide a configuration. Once that configuration is provided, map loading will happen for you. No need to write that boring Java code over and over again, or worse, copying it from Stack Overflow. So in the new management center, you get this overview of SQL, which is even able to help you out with constructing some of the basic constructs. And this is pretty exciting. But what's even more exciting is that alongside IMDG, we've developed a different product called Hazelcast Jet, which was a real-time streaming engine. And that paper should be especially interesting for you because it was developed in times when no one actually dreamt about Project Loom making it to Java. There were some rough ideas, but no one actually thought it would be that fast. So the team working behind that, they needed pretty much implement their own engine, Loom-like an execution engine. And this white paper pretty much explains how it was done. What's more, we are trying to go public with our design docs. So if you are interested in how those things work internally, or at least learn from them, it's all public. Well, maybe not all of them, because sometimes we might have forgotten about a few of them, but most of them are public. And if you want to see more potential use cases of what you can do with streaming, it's available out there. There are demos and examples. With the first one being Bitcoin Death Cross, which feels relevant nowadays. And to give you a bit more indication, I remember a couple of years ago, I worked on a project where we actually tried to implement real-time streaming. And to give you an idea how this could look like, our project was for a big Polish telecom. And they came up with an idea. They noticed something interesting. So they noticed that people procrastinate, especially with buying their roaming packages. So they started tracking how MSISDN numbers connect to BTS stations. And if they notice a pattern that someone is getting closer to the border, it's quite likely they procrastinated and didn't get the roaming package. So then when they would be issued a one-time limited offer to get their roaming package at discounted price. I'm not sure, I don't know the sales numbers, how it worked out, but I heard it was pretty successful. But Hazelcast Jet, the streaming engine, used Hazelcast internally for its own, to make sure to keep the state. So if someone wanted to use Hazelcast Jet, they still needed to somehow deal with their IMDG itself. So we figured out, well, if those projects are coupled together, let's actually merge them together. And since Hazelcast 5.0, Jet and IMDG are one single product called Hazelcast Platform. And that opened up pretty interesting opportunities, because we've had customers running on 4.x. They upgraded to 5.x. In the market, that's a bit commoditized when it comes to caching. And suddenly, we were able to go to them and look, you have all this data in there. Let's do something cool with that. And we were converting them from someone using just a cache, but trying to leverage real-time streaming capabilities of the data that's constantly changing in the cluster itself. So, as you can guess, if you want to be successful with tools like Hazelcast, you need to understand how to properly tune it. So, for example, auto-scaling. You need to answer a couple of questions. So, how much data do I want to store? And if I want to store that much of data, how many backups do I want to have? Do I want to have those backups asynchronous? How many nodes do I want to have persistence on? Do I want to have other stuff? And suddenly there's quite a lot of decisions to make. You need to understand how the product works. So that's where we figured out, hey, we need a product that's as easy as possible to run. So we shipped Hazelcast Viridian. It was released not that long time ago. This Viridian is a code name for the cloud product, which is an opinionated view over Hazelcast. So when you get that, and you can register using GitHub pretty much for free right away. There is limited time offer, a few gigabytes for free. You don't think in terms of members. You don't think in terms of backups, member sizes. The only abstraction that you are supposed to use is data. So when you go there, you think, OK, I want to store 1 gigabyte of data, 5 gigabytes of data, and that's all that you need to set up. And we'll figure out the optimal way of running it for you. So it's an opinionated version of Hazelcast focused on developer experience. And it's already out there. So change data capture became quite possible, and Hazelcast Jet did support change data capture from various data sources. However, we overlooked that you couldn't really do change data capture on the Hazelcast itself. So we figured out it's time to add it back. And at the beginning, I told you that hardware is catching up with, hard drives are catching up with RAM. So we are experimenting and playing around with an idea of tiered storage, which will be available as preview in tomorrow. And the idea is that if there is too much data in your Hazelcast member, let this data spill over to disk. So instead of being limited to hundreds of gigabytes on a single member, suddenly you can go to terabytes. Potentially playing around with the ratio. So if you, for example, don't care that much about super low latency, you could go for the ratio where just a small subset of hot data is kept in RAM, but most of it is kept in disk, which would be way cheaper for you. And here comes the end comes the fun part, which means next generation of Hazelcast. Hazelcast 6.0, which we call internally Project Alto. It's a set of initiatives that we are that's supposed to revolutionize the product altogether. If you've heard about ScyllaDB and what they did to Cassandra, or Red Panda and what they did to Kafka, we are kind of planning to do the same thing with Hazelcast. It's just the difference, it's going to be us and not someone else. And the main difference they did is they rewrote the internals from stage event-driven architecture, remember those couple of thread pools connected by queues, to thread per core idea. It's a very simple idea. So instead of having just so many thread pools and queues and wasting so much time on synchronization, let's create the number of threads which is exact as the number of cores. Let's throw in pinning, thread pinning to cores into that, and let a single thread do all the job. Let it read from the socket and write to a partition. And it turns out, if you do it with a mechanical sympathy in mind, you can get throughputs and latency orders of magnitude better than in the old setup. Because in such setup, there's almost close to zero concurrent code. If you remove all the allocations from the hot path, this thing can get really fast. And if every core is owning its own partition, there's no need to have any synchronization in there. So it's not just performant, but also boring simple, because you can assume it's just single-threaded within the scope of one partition. And we have some initial prototypes, and it's super promising. The other thing is, hardware is catching up. We're building tiered storage. But with this thread per core rewrite, perhaps we could go storage first. If we go for that thread per core idea and throw in some asynchronous I/O with I/O U-ring bindings, you can get pretty decent performance. So perhaps it's quite an option that we might be storage first in the future, with only small subset of data being kept in memory, like databases do. However, our legal team would probably advise me to say at the beginning of the presentation at the time that all I'm saying here is a lie. So keep that in mind. Another thing is, so once we are going storage first and thread per core, it would be cool to have one more thing. Schema in Hazelcast now is a kind of something that is derived from data that you put in there. You never start with a schema first. But this allows so much simplification, not just from how SQL works, but also once you control the layout of all the data, of the layout of what you keep in memory, that allows optimizing it and squeezing some extra performance from that. So I think that this is also what's very likely to happen in the future. And one more thing that we'll probably experiment with is that we'll probably make it available in the cloud in Viridian as soon as possible. So once we have the prototypes ready, there will be probably, so far, those prototypes will rely heavily on enterprise features, which are not open source. So we'll make it public as soon as possible via the cloud, with eventually rolling it out to normal Hazelcast. So that's what we'll be playing with and trying to experiment. And that's pretty much all that I wanted to show you today. And I hope you learned something new about the product. So that's a QA time, and let's find those Slido pages. Give me a second, I need to unmirror my... what was the link? Okay. Yeah, but okay. Okay, fair enough. Okay, anyway, so if you want to ask some extra questions, I'm here. I don't bite, so just grab me on the corridor and I will gladly answer some. Okay, thank you.